Welcome to the video lecture on properties of logarithms. So today we're going to learn about three important properties of logarithms that will help you to simplify expressions involving logs. Now, because logs and exponents are inverses of each other, they should share similar properties. So our properties of logs should parallel the properties that we already know for exponents. So let's review the properties that we already know for exponents. The first one says x to the m times x to the n equals what? Here we're multiplying common bases, so what do we get to do with the powers? We get to add them. So this becomes x to the m plus n. For the next one, we're dividing the common base, so what do we get to the powers? We get to subtract them. So this would be x to the m minus n. And finally, this last property is like a power to a power, and in that case we get to multiply the two powers together, so this would be x to the m times n. So our properties for logs are going to be similar in that they're going to take products and change them to additions, quotients, change them to subtractions, and powers being multiplied. Okay, so let's talk about our three properties. First of all, we're going to assume that the base a is a positive number different from 1. The x's and the y's are numbers that are greater than 0, and c can be any real number. So our first property is our product property for logs, which says that the log base a of the product of x times y becomes the log base a of the x plus the log base a of the y. So we're basically splitting up this product, this multiplication, and turning it into a sum of two logs, just like we did up here with our exponents. Similarly, the log base a of a quotient of x divided by y becomes log base a of the x on top minus the log base a of the y on the bottom. So a quotient, division, turned into subtraction of logs. And here, this quotient turned into subtraction of powers. And finally, log base a of x raised to a power c. What do we get to do with that power c? We get to bring it out front and multiply it by our log. So this becomes c times log base a of x. So those powers get multiplied down up front, just like our powers got multiplied over here. Now the proofs for all three of these are very similar, and we're just going to prove the first case here. So what we're going to assume for our proof is we are going to let log base a of x represent capital A, and I am going to call log base a of y capital B. Because of our inverse relationship between logs and exponents, then this logarithmic expression right here could be rewritten as a raised to the capital A has to equal x, and this one could be rewritten as a to the capital B has to equal y. These are equivalent statements because logs and exponents can be written in both forms. So what we're going to do now is we're going to try and prove this property 1. So I'm going to start with this left-hand side, this log base a of the product x, y, and I'm going to try to figure out what it equals. So what I'm going to do is replace this x with a to the a, and I'm going to replace the y with a to the b. So this expression becomes log base a of a to the capital A and a to the capital B. And then, because of our properties of exponents, these two bases match, so a to the a times a to the b becomes a to the a plus b. And then, because of our properties of logs, in the fact that if your base of your a matches the base of your exponential, these are going to cancel each other out and give you back just this power on top. And this was discussed in a previous lecture. But another way to visualize that is if you're trying to figure out what log base a of a raised to the a plus b is, a raised to what would give you back a raised to a plus b. It has to be that power. So that's why these cancel out, giving you just that power back again. So we have the right-hand side now equals capital A plus capital B, and what did capital A represent? Well, going back to the beginning, capital A is what we called log base a of x, and capital B was what we called log base a of y. So we just showed that log base a of the product is log base a of the x plus log base a of the y. So that's the proof for property 1. Now let's apply these properties. So we're going to write each of the following expressions as a single logarithm, and we're going to assume that any variables are always positive so that we're not having to worry about domain issues. So in these set of problems, what's common is that you've got many logs and you're trying to consolidate them down to a single log. So you're trying to simplify these expressions. So if we take a look at this first one, we have log base 2 of 9 plus log base 2 of 3. The fact that they're both base 2 is very important because otherwise we wouldn't be able to do anything with this problem. But since the bases match and we have a sum of the two logs, this is going to be that property 1 in reverse. We have this right-hand side already, and what we're going to do is combine the two logs that are being added into a single log by multiplying their arguments, by multiplying their stuff. So these two combine into a single log base 2, and to do that we have to multiply their two arguments together. And 9 times 3 is just 27, so this simplified would be the same as log base 2 of 27. So now we're going to do that on number 2 as well, and there's 3 of them here, so you could really do this in any order you like. Addition is commutative, so it doesn't really matter which ones you do, and you can do them all 3 at once, or you could do 2 at a time. So let me just show you, if we did it 2 at a time, if I take these two logs, and notice again they're all log base 6s, which is important, then I can combine the sum of these two logs into a single log base 6 by multiplying this stuff times this stuff. And I'm going to put the 3 in the front just to make it look a little cleaner. So this would be 3 times x squared plus 1. And I still have this log base 6 of x left over that I haven't used yet. So now if I combine these two together into a single log, it's log base 6 of all of this stuff times x, times this stuff. And then just to make it even nicer, you can think of this as 3x, a single 3x, and we're multiplying it across those parentheses. So 3x times x squared is 3x cubed, and 3x times 1 would just be 3x. So it's up to you how far you take it, but that looks pretty good to me. That looks pretty clean. Now if we take a look at the next example here, now we have subtraction. So in order to combine these two logs into a single log base 7, because it's subtraction, that changes to division of their arguments. The first argument, the 20, goes on top. The second argument, 4, goes on the bottom. And if we simplify that, 20 divided by 4 just becomes a 5. So this is the same thing as log base 7 of 5. Now on the next example here, we've got a mixture of things. We've got a sum. So these two arguments can be combined by multiplying them together. But if you look at this last ln, it's being subtracted, which converts to a quotient, but there's also a coefficient in front, and we haven't had to do one of these yet. This is going to be that property 3 in reverse. If we have a 2 in front, in order to make it similar to these other ln's which do not have coefficients in front, we're going to need to remove that coefficient by moving it back up to this power, just like we do in this property 3. So I want to make all the coefficients in front of these ln's be the same. In other words, I want to make them all 1s. So to do that, I'm going to move this 2 up to the power on that c and rewrite this as ln of c squared. That's that property 3 in action. And I'm just going to rewrite these other two pieces. Now if I combine these two together, I'm going to get ln of the a plus the b, this stuff, times this stuff, a minus b. If you want, you could FOIL that out. It is a difference of squares, so it becomes an a squared minus a b squared. And then finally, these two are being subtracted, so this is going to become a single ln, and because it's subtraction, that turns into division. The a squared minus b squared goes on top, and the c squared goes on the bottom. Now we wouldn't be able to do that subtraction turning it into division unless these coefficients in front of these two ln's were the same. That's why I had to move that 2 up to the power first. Now the next three examples are pretty common problems. You see these in most textbooks, so you'll want to know how to do these kinds of problems, but they look a little bit strange. What we have here is sort of this mysterious base b that we know nothing about, except that we happen to have two values that are known to us. We're told that log base b of 3 equals 0.5 and log base b of 5 equals 0.7. So just based on those two pieces of information, we are going to use our properties of logs to manipulate those and come up with these three values of these logs down here. So let's start with log base b of 25. In order to figure out log base b of 25, we need to make it look like either a log base b of 3, since we have a value for that, or a log base b of 5, since we have a value for that. Now I don't know how to take 25 and turn it into a 3, but I do know how to take a 25 and turn it into a 5. All I can do, or what I can do here, is break up this 25. Now there's a couple ways to do it. You could either think of 25 as 5 times 5, or you could think of 25 as 5 squared. Both ways will give you the same answer. If I change it to a square, then we can then bring that power down using properties of logs and rewrite this as log 2 times log base b of 5. And I know exactly what the value of log base b of 5 is. According to this, it's 0.7. So we can substitute in 0.7. That has to get multiplied by that 2. So this answer must be 1.4. So even though we didn't know a whole lot, we were able to get an additional value of this log because we could manipulate it to look like one of these two that we started with. So we're going to do the same thing here in number 6. We have log base b of 9/5, and you want to somehow break this down so that its pieces look like log base b's of 3 or log base b's of 5. And you can kind of see where that might come from. First thing I'm going to want to do is break up this quotient. So we're going to use this property number 2 as it directly is. So I'm going to take this quotient and I'm going to split it up into the difference of two different logs, log of the top minus the log of the bottom. So this becomes log base b of the top 9 minus log base b of the bottom 5. Now the log base b of 5 I already know, that's 0.7. But this one I don't know yet. However, kind of like in the last example, we can change this 9 into a 3 squared. And then we can bring that 2 out front, so this becomes 2 times log base b of 3. And now that I have all of it broken down, this piece I know is a 0.5, and that's getting multiplied by 2. And this piece I know was that 0.7. So 2 times 0.5 is 1, minus 0.7 gives me 0.3. Okay, on the last one here, we have log base b of the cube root of 5 over 27. So the first thing that I see is this big cube root. It's kind of in my way in terms of getting at that 5 and that 27. So the first thing you want to realize is that a cube root is the same as a power. What is the power that's equivalent to a cube root? Cube root is a 1/3 power. So what I'm going to do is rewrite this as a 1/3 power. And if I have a power, I can always bring that power out front. And now we're going to do like we did on the last example. We're going to split up this quotient. So it's going to be the log base b of the 5 on top minus the log base b of the 27. Now notice, we wanted 1/3 of that whole log up here, so I need 1/3 of this entire difference. So you have to use parentheses here. Now the next thing is, I know what log base b of 5 is, but I don't know log base b of 27. So 27, you have to think of it as a power. It is a 3 cubed. 3 cubed is 27. And once I know that I've got a 3 cubed, I can bring that 3 down, and this becomes log base b of 5 minus 3 log base b of 3. So if I plug in my numbers now, I'm going to have 1/3 of log base b of 5 is 0.7, and 3 times log base b of 3, that was 0.5. So if we dig out the calculator here, we want 1/3 parentheses 0.7 minus 3 times 0.5, close the parentheses, hit enter. There it is as a decimal. If I wanted to know what this was as a fraction, I could just hit math and use that frac button right at the top, hit enter, and it's going to turn my last answer that's a decimal into a fraction. And I kind of like to use fractions because it's a little more exact. You don't have to round off your decimal. So this is the same as -4/15. Okay, so in the last few examples before the ones we just did, we were taking many logs and consolidating them down to a single log. Now we're going to go in reverse. All of these are a single log, and we're going to sort of expand them out into a bunch of sums or differences of logs. So we're just going in the opposite direction. So if you take a look at this first example, I see a quotient, and we know that we can break up a quotient by changing it to subtraction. So this is going to become log base 4 of the top, which is the 2, minus log base 4 of the bottom, which is that 9z. Now you could stop here, but you could also realize that 9z is really a product of 9 times z. So that product can be broken down into a sum. So this becomes log base 4 of just the 9 plus log base 4 of just the z. Now one thing you have to be careful about, remember up here we were subtracting this entire log base 4 from the log base 4 of 2. So we want to subtract both of these because both of them came from this piece up here, from that log base 4 of 2. And it's a good idea to go ahead and distribute that negative across. So this would be log base 4 of 2 minus log base 4 of 9 minus log base 4 of z. And one thing I want to point out here that you can use as sort of a shortcut is if you have a quotient like this, what you want to notice is that any expressions that come from the numerator will always result in positive logs. This was a positive log right here. But any pieces that come from the denominator should have minus signs in front of the log. So the 9 had a minus in front of its log, and the z had a minus in front of its log. So anything from the top should be positive. Anything from the bottom should be negative. All right, let's try the next one. Now, in order to break this up, we do want to get at that quotient, but before you can get at that quotient, you have to get past that square root. So the first thing you're going to have to do is change this square root to a power. And remember, radicals are always fractional powers. So if this is a square root, this is the same as a 1/2 power. And powers are good with logs because you can always bring that power out front. So this becomes 1/2 times log base b of 3 over y. Then we can break up that quotient into a difference of two logs. So log base b of the top 3 minus log base b of the bottom y, and it's 1/2 times both of those. So you can either leave your answer like this, or you could distribute that 1/2 across. That's up to you. And the 1/2 would then become coefficients in front of both of those logs. Okay, the next example here, we want log base b of this quotient here. Now this is a quotient, so we know that that's going to turn into subtraction of two logs. One thing you want to be a little bit careful about is this power. Sometimes it's tempting to see a power and automatically bring it out front. But we can't do that on this particular problem yet because that power isn't on the entire quotient, it's just on the numerator. It would have to be written as this in order for me to bring that 2 down. I'd have to see parentheses around the x plus 5 and the x. But since I don't have that, then we're going to have to break up the quotient first and then deal with that square. So this becomes log base b of the top, x plus 5 quantity squared, minus log base b of the bottom, which is just an x. Once we've split up that quotient, then I can bring this power down. So 2 log base b of x plus 5 minus log base b of x. And that's your final answer. One thing I want to make a note about that sometimes is confusing for students is right here, you cannot distribute that log across. So log base b of x plus 5, you're not allowed to take the log of each piece because that's just not true. It doesn't match up with our properties of logs that we already know about. If we thought it was this side, then you could think about this as being a sum of 2 logs, and according to our properties of logs, the sum of 2 logs is supposed to be the product of their arguments. So this should be log base b of 5x, which is not the same thing as x plus 5. So it's not allowed to distribute logs across plus or minuses. Okay? Alright, the last one here is pretty messy looking, so let's see if we can handle it. We have this great big quotient, and there's lots of different powers going on. So we want to deal with the quotient first to break that apart, and then we'll deal with the powers. So we want the ln of the top, so that's this z 4th root of x, minus ln of the bottom, which is this great big cube root. Then on this first expression here, you need to realize that this is z times a 4th root of x, and a product becomes a sum of 2 logs. So this is going to become ln of just the z plus ln of the 4th root of x. And then finally, now that we have all the pieces sort of separated from each other, now I can deal with these roots that I have. I don't have any power on that z, so I'm just going to leave that one the way it is. But this 4th root of x could be thought of as an x to the 1/4. And this cube root can be thought of all this stuff raised to the 1/3. So then I can bring those 1/3 and those 1/4 down out front. So my final answer becomes ln of z plus 1/4 ln of x minus 1/3 ln of this entire quadratic. And based on what we just talked about in this last note over here, you're not allowed to distribute those ln's across because you see addition in between your terms. So your answer would just be this whole big expression. Okay? Alright, the last thing that we're going to talk about is this change of base formula. If you recall in your calculator, there's only 2 types of logs that you're allowed to do on your calculator. log, which stands for a common log, which is log base 10, and ln, which stands for natural log, which is log base e. So if you needed to know, for example, log base 2 of 5, for example, and you needed to know what decimal that was, there is no button on our calculator that lets us do a log base 2. So the way to get around that is to use this thing called the change of base formula. And it's pretty simple, but you just have to remember where things get placed. If you have any expression of the form log base b of x, then what you can do is change it to any base you want, and that's what this a is here. So any base a that you choose, the x, this argument here, goes on the top, and the original base that you had to begin with goes on the bottom. So in other words, log base 2 of 5 could be rewritten as the log of my choice. So let's say I wanted to use an ln. So you would use an ln on the top and on the bottom. The 5 that's the argument is going to go on the top, and the 2 that was the original base would go on the bottom. Now let's say I didn't want to use an ln. Let's say I wanted to use a common log. Well, that's okay, you can. You would still put the 5 on the top and the 2 on the bottom. And we'll see in just a minute that both of these 2 ratios, these 2 fractions, end up giving you the same decimal. So even though I can't directly type in log base 2 of 5, I can type in those 2 ratios of ln of 5 divided by ln of 2. Or I could have done log of 5 divided by log of 2. And no matter which base I had chosen, notice we still get the same decimal back again. So I am able to get a decimal value for this log even though it had one of our uncommon bases. And you can do it using ln's or using logs, it doesn't matter. Okay, let's take a look at the relationship between log base a of b and log base b of a. So what I'm going to do to figure this out is I'm going to start with log base a of b, and I'm going to use my change of base formula on it. So I'm going to change this to the log of my choice, and the choice of base that I'm going to use is base b. This b, that's the argument, goes on top. This original base here goes on the bottom. And what you'll notice is we get log base b of b on top. Well, what is log base b of b? To figure it out, think about it in reverse in terms of an exponent. B to the what gives you back b, b to the first. So log base b of b just becomes 1. And on the bottom we have log base b of a. So what we have found out here is that log base a of b, that's what we started with over here, is just 1 over log base b of a. So they're reciprocals of each other. So that's the relationship between the two. Alright, for the last ones here, let's go ahead and evaluate some of these using our calculator. So this first one is log of 27. Remember, log, if there's no base written there, that's implied to be base 10. So this one we can just do right on our calculator because I can just hit log 27. If you leave off the parentheses, that's okay. It'll let you get away with it. And just hit enter, and we get 1.431. I like to give at least 3 decimal places. The next one here is ln of 142, and that's also one of the buttons we have on our calculator. So if I do ln of 142, hit enter, and I get 4.956 if I round off, which is always a good idea to round off. 4.956. Now these last two are log base 6 and log base 8, and we don't have buttons for that on our calculator, so we will need to do a change of base. And if we want decimals, then you're going to have to change to either a log base 10 or an ln, because those are the only 2 bases that we can compute on our calculator. So let's do this first one with a log base 10. So it becomes this ratio of a log over a log. The argument that's here goes on top, and the original base goes on the bottom. So on my calculator, whoops, I would have, there we go, we would have log of 40 divided by log of 6. And we get 2.059, rounding off. For this one, let's change them to ln's this time. So I get to choose my base. I'm going to choose them to be both ln's. This argument goes on the top, and this original base goes on the bottom. So I need ln of 100 divided by ln of 8. And I get 2.215. Okay? Then the very last problem says to find the exact value for log base 2 of 5 times log base 5 of 7. So this is one that I would expect you to be able to do without using your calculator at all, because something kind of clever is going to happen here. But the key to being able to do this is to use that change of base formula. So log base 2 of 5, how could we rewrite that using a different base? You get to choose what base you want to use. It's up to you. So let's say we chose log base 10, so log. Then log base 2 of 5, I would put the 5 on the top and the 2 on the bottom. Now let's do the same thing for this second log here, this log base 5 of 7. Let's do a change of base on it using the same log that I used over here. So I'm going to use log base 10 again, and the 7 goes on the top and the 5 goes on the bottom. And we're multiplying these two things together. So the reason why this turns out really slick is if you look, we're multiplying these two tops and these two bottoms, and these two, this top and this bottom, match exactly. So you can go ahead and cancel them out. So this becomes log base 7 on top over log base 2 on the bottom. And you could leave it like that, but it's much slicker to kind of rewrite this as a more simplified log using that change of base formula in reverse. So now what I could do is rewrite this as a single log. Remember that the number that's on top comes from the argument, and the number that's on the bottom is from the original base. So this is really the same ratio as log base 2 of 7. So we were able to figure out that this is log base 2 of 7 because these 5s essentially cancel each other out. But the reason why is by this work that we've just shown here. Alright, good job. That concludes our lecture on properties of logarithms.